Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section of the class, we're going to switch gears yet again and start to begin to talk about a new topic entirely, and that's the topic of polar coordinates. So the next 2 or 3 sections are going to deal with polar representation of functions, and this is the introductory part of that, dealing with polar coordinates. So in this class has sort of been a hodgepodge of things, and that's how Calculus 2 is when you get toward the end of it. You start to talk about your trigonometric functions, your inverses. You start to talk about all of your surface areas and your arc lengths and all that stuff sort of disconnected. And then you come into the topic of polar coordinates, polar equations, and specifically the culmination of that in Calculus 2 is doing the integrals in polar coordinates. And sometimes that can trip people up because it's a new concept. It's not something you're used to thinking about too much. But I have to say that this polar stuff, all of this stuff is somewhat important if you're going to go on to engineering or physics or any kind of a science-based career, okay? But polar coordinates, I really want you to learn this stuff, okay? Because having gone through engineering and gone on and done some things, really that is very powerful stuff. And some of the other topics in this class, you may or you may not ever use them in your whole life. Some of the topics on the techniques of integration by partial fractions, you may not use that. It just depends on if you happen to come up against a problem to need that. Polar representation and polar integration and all that stuff, that is used pretty much all the time by any branch of engineering that you go into. So this is really important stuff. So let's just dive right into it. What we're talking about now, we're not talking about any integrals, we're not talking about derivatives, we're not talking about anything other than in this section talking about what a polar coordinate is, okay? So remember that a Cartesian coordinate, or a Cartesian coordinate is the one that you've learned about all your life. You have two numbers, x and y, that define that. So if this is your graph, that you've grown up knowing all the time, it's the xy graph, right? And I have a point here, okay? And when you learned about this point, you were taught that this point can be represented by two numbers, x, comma, y. Okay, now you're very comfortable with this idea now because you've been doing it for so long. But when you were first introduced to this, this was a pretty far out concept, okay? That you would take a point, you'd put it on a graph, and that location of that point would be the x coordinate, and you'd put a comma here, and then you'd also put the y coordinate. And those are just numbers. It could be 3, 4, 2, 5, -1, 2, whatever it is. Two numbers to represent a point in a plane. And as you know, when you get into talking about three-dimensional functions in three-dimensional space, which is the real world we live in, when you get off to Calculus 3 next semester, you're going to have a third dimension there, so it'll be x and y and z. But for now, everything we're talking about is only in a plane, okay? Because that makes it easier. Okay, so here are our points. These are Cartesian points. Those are the ones you already know about. And you write equations. Equations in Cartesian coordinate systems they're very simply the same sort of thing. You have x and y, all right, on a graph, and then if you have some sort of function, it would go up and come down or whatever it does, some smooth continuous function, okay, and we say that y is equal to f of x. Now, this is all review here, okay? This vertical direction here, y, that shapes what this graph actually looks like, is a function of x. You take a value of x, you stick it in this function, you get back the value of y, okay? So we say here that x is the independent variable. And that's because that's the number you actually plug into the function, so it's independent. The dependent variable is y because it's dependent on whatever value of x you have and also on the function that you have. Okay, so these are Cartesian coordinates, okay? You have when you want to plot one on a graph, you go over x number of units and you go up y number of units, and it takes two numbers to uniquely define any point in that plane, okay? Now, polar coordinates also take two numbers to identify a point in the plane, okay? So it's two numbers, so it's really not that different. You're still going to have a number, comma, and then another number to represent that point. But in the Cartesian space, in the polar space, that's going to look a little bit different, obviously. So you're still going to have a plane like this, and you can still call this x and you can still call this y, just for reference, okay, just for reference. But if I have a point here, and notice up above, I called that point x comma y. This point would be labeled by or defined by two numbers, and those numbers are going to be r comma theta. okay? R comma theta. What does that mean? So I can define this point, instead of marching over so many units and then marching up so many units, those being the numbers, I can define this point as a radius, r, that's just the length of some arrow that I describe, and I can also define it by the angle that this radius vector, or this radius line segment here, forms with the x-axis. So you see it's two numbers, okay? It's two numbers, and by the way, it's always going to take two numbers to uniquely define a point in a two-dimensional plane, because you only have two dimensions in that plane, so no matter how you define your coordinate system, you're always going to need two numbers. When you have three-dimensional space, you're always going to need three numbers, and so on, okay? So in this coordinate system, and I'll just go ahead and write it down, just so you know, for the polar representation of coordinates and polar coordinates, okay? Every point in this plane can be defined by two numbers. The first number is the distance from the origin, basically. So wherever this point is, it's the distance to the origin. That's what we call r. And then the second number is the angle that that vector makes here with the point, okay? So you could see that if you had a point anywhere, you could have another point over here. Well, I could define, well, that's too similar. Let's make it way over here. I could have a point over here, like this, and I could have an r, that would be the length of this vector, and I have an angle that this thing forms with the x-axis. So the angle would be this giant open angle here. Theta is always in reference to the x-axis. So if I have a point way down here, the angle is going to be all the way over here, you see? So that's how you have to do it. That's what polar coordinates are, okay? So it's reference to the x-axis. Those are for positive angles, okay? Now you can always have you can also have representation of negative angles as well, okay? If I wanted to use a negative angle, I could also do that, okay? So it would be r, and then I would have a negative angle, okay? So the angle can be expressed either by going all the way around to that place, or by just using a negative angle. So these are all positive directions, and these are all negative directions in the angle, okay? So two numbers, not that terribly different. It's just a little bit different way of looking at it. Now, why do you think you would do that, by the way? Why do you think we would ever use polar coordinates, okay? The reason is usually you're using a polar coordinate system when you have something circular that you're studying. And gosh, there's millions of applications for it. I mean, you could be studying, let's say, the physics of the surface of a drum, okay? Or maybe a raindrop dropping in a puddle of water and the waves that come out from the center. See, you have circular symmetry like that. So anytime you have circular symmetry, anything circular, where you know, the equation of a circle in Cartesian coordinates is kind of ugly, but in polar coordinates it's very simple, and because of this nice symmetry, you can have easier and simpler integrals. So yeah, you have to have a little overhead learning what this stuff means, polar coordinates and polar equations and polar integrals. We're going to get to all that stuff, but once you know it, it really makes the math a lot easier than actually trying to do these integrations and these other things in Cartesian coordinates, okay? So let me show you one more thing. Here's an example, an additional example of polar coordinates, okay? Let's say I have an XY plane for reference, okay? And let's say my point is actually up here, just like this, okay? And this point, I'm going to say, it is a distance of 1 from the origin, okay? And the angle here, theta, is equal to pi over 4. So you should know pi over 4 is 45 degrees. So all I'm saying is that 45 degrees from the x-axis, 1 unit away, there is a point. So it's two numbers. This is my polar representation. So the polar representation, okay, of this point is just what we talked about before. It is r comma theta. So it's 1 comma pi over 4. So that's how you would write it down in your test or your homework. That's how you would see it in your book. It would be the radius, comma, and then the angle. That's how you write it down, okay? Just like it's always x comma y in the books, you know, for Cartesian, it's always r comma theta, okay? Now, let me ask you this. This is the location of the point at pi over 4, okay? Now, you should know from your trig and your introductory calculus and all of that, you know, in trig, in radian angle measure, you can continue on past pi over 4, and you can go all the way around another full circle and arrive back at the same point. And one full circle in trig is always 2 pi radians. Any circle you make is always 2 pi radians, okay? So in theory, I could add another 2 pi radians to this angle, and I would end up in exactly the same place. So what would that look like? Okay, so what I'm trying to say is that this representation is equally valid equally valid representation at plus or minus 2 pi angles. Now, what do I mean by that? Let me switch colors and show you what I mean by that, okay? This is the polar representation of this point that we already talked about. Now, I can also say that that's going to equal pi over 4, which is my angle, plus 2 pi. Okay, so it's the same radius, and it's the same starting angle. But what I'm saying is if I add 2 pi, I come back to exactly the same spot, so it's really the same point. Okay, so if I were going to simplify this, it would be 1 comma pi over 4. And how would I write 2 pi in order to add these fractions together? It would be 8 pi divided by 4. 8 pi divided by 4. I chose it this way because, look, 8 pi divided by 4 is equal to 2 pi. I wrote it this way because I want to add these fractions. Okay? So that would be equal to 1 comma 8 pi plus pi is 9 pi divided by 4. 9 pi divided by 4. So what am I trying to say here? I'm trying to say that this polar representation, which is 1 radius of 1, 9 pi over 4 radians, is exactly the same point. It represents exactly the same point as this one. The angles look different, but the only difference between them is that I've gone an entire circle around again. So it's really exactly the same thing. So any polar representation you have, you can always add or subtract 2 pi. In fact, you can add or subtract increments of 2 pi, and you'll get a different looking answer, but it'll represent the same point. Okay, I can take this initial point that I had, pi over 4, okay, and instead of adding 2 pi, I can also add 4 pi to it. Because think about it, 2 pi goes around once, and then another 2 pi goes around again. So I can add 4 pi to it, and what would that look like? It would be 1 comma pi over 4, and I'm going to add to it, 4 pi, but that's going to be 16 pi divided by 4. I'm writing 4 pi as 16 pi over 4 because I want to have a common denominator here. So 16 pi over 4, when you do this division, is equal to 4 pi. Okay? So what would that be? That would be 1 comma pi plus 16 pi is 17 pi divided by 4. Okay? 17 pi divided by 4. Okay? So this representation, 1 comma 17 pi over 4 for the angle. This representation, 1 comma 9 pi over 4. And the original representation, they look different, but they're exactly the same thing. They have different angles, but because the angles are just 2 pi going around the circle 2 pi, which is a full circle, they actually describe the same thing. So, and the same thing goes for subtracting 2 pi and subtracting 4 pi and subtracting 6 pi and so on and so on. So I'm adding them here, but you could just as legally subtract 2 pi. So instead of adding 2 pi, I just subtract 2 pi. Okay, and I get back to where I started from. So any polar point you have, you can always add to any multiple of 2 pi, 4 pi, 6 pi, 8 pi, so on. You can also subtract them the same way I'm doing here, and you'll get different points, but they're going to all represent the same thing. Okay, so the long and short of it is, the thing that I want you to take home is that polar representation of points have infinite number of representations in polar coordinates, and they're all equally spaced by 2 pi radians. So for any point you define, and that's different than rectangular. In rectangular, it's x comma y, and that's it. In polar, it's r comma theta, but there's actually infinite variations that I can write, and they all represent the same point because the angles can be manipulated like this. Okay, so we've introduced the concept of the polar representation of a point. Okay, we've done that. So we know we have this Cartesian thing, x comma y, and we know we have this polar thing, r comma theta. We know that there are two different ways of writing exactly the same thing, which is just simply trying to describe the location of a point in space. That's all it's trying to do. It's just different ways of doing it. Okay, so naturally, it's something that you would like to be able to do, to be able to convert between the two representations, right? I mean, some engineer might be working in x comma y, and you might get his work and say, well, that's nice, but it would really be a lot simpler if we just worked in polar coordinates. So you'd be able to take his work or her work, okay, and convert it into polar coordinates, and then continue on from there and do your own work. And likewise, you might be working in polar coordinates, and then somebody comes back and says, well, that's nice, but I need to work in Cartesian for whatever reason, and it would be nice if you could convert all of his work into Cartesian. And it should be possible to do this because they're just two different ways of saying the same thing. So it's just like converting from miles to feet or centimeters to kilometers. You can do it, it's just you have to know how to convert them. So that's what we're going to be able to do here. We're going to learn how to convert these things. Okay, so to go from, I'm going to do the easier one first. To go from, they're both actually pretty easy, but one of them is actually a little bit easier. From polar, and just to remind you, that's r comma theta, okay, to Cartesian, okay, Cartesian, which is x comma y, just to remind you, to go from polar coordinates to Cartesian coordinates. So I'm given r comma theta, and I would like to convert to x comma y. We'll go ahead and write it down. I'm going to show you why. The x coordinate, I'll go ahead and change colors here, just to make it clear. The x coordinate is going to equal r times cosine of theta, and the y coordinate is equal to r times the sine of theta. That's all you have to do to convert from polar coordinates to rectangular coordinates or Cartesian coordinates. Because if I'm given a polar value, okay, and I'm trying to convert it here, I know what r is, so I know the distance from the origin, and I know the angle, which is just the angle from the x-axis, either positive or negative, okay? And so I know what r is, and I know what theta is. I just plug it in here, and I'll get an x, and I plug it in here, and I'll get a y, and that's the corresponding x and y. Now, why does this work? Why does this work this way? Well, if you remember back, let me just draw a quick little picture here to the side. Okay, if here's x and y, and here's the point I'm interested in, okay? And obviously it's going to have a radius here and an angle here, okay? Well, what you're doing here, you see, this is r and theta that I'm given, and I'd like to convert to Cartesian coordinates, okay? So what I've claimed here is I'm telling you that this x value, okay, this x value of this point is equal to r times cosine theta. So I'm saying this is r times cosine of theta, okay? And it's this way just because, you know, when you think back to your trig, you know, or you should know if you don't already know, that the cosine function, what it does is it's, you know, forgetting about this, the cosine of something, when you march around the unit circle and you start taking the cosine of something, like cosine of 0, you know it's equal to 1. Because you're looking at the projection of that unit circle radius onto the x-axis. That's what you're doing. So as you take angles around the origin, all you're doing is you're looking at the projection along the x-axis. And you're talking about a unit circle, so in that case, the radius is always equal to 1. So in this case, you're just generalizing it, and you're saying, well, the radius is no longer equal to 1. The radius is whatever it is, because I'm talking about an arbitrary point. So I'm looking at the projection of this thing onto the x-axis. So it's still cosine theta, but I'm just multiplying it, scaling it by r. Okay, that hopefully is very clear to you, but if it's not, you could also just use your regular trig here. Some people like to write it this way. Cosine of I keep writing a theta here. Cosine of theta, you could say cosine of theta is equal to the adjacent value over the hypotenuse, okay? The hypotenuse is r, right? So you could say r. Here. So if you were to solve this thing for the adjacent value, which is this, which is what you're trying to find for the value of x, it would be r times cosine of theta, okay? So it's really just triangle trig is all it is. That's all these things are right here. And so by analogy, the same exact thing is true here. This value, which is the y value of this point, is equal to r times sine of theta because you're looking at the projection of this on to the y-axis. And it's the same thing as before. The sine function, you should know, in general, is the projection of that unit circle onto the y-axis. It's just here, it's not a unit circle. It's an arbitrary length r, depending on where the point is. So you're doing the same thing. It's sine of theta, and you're multiplying by r because you're scaling it, okay? So this is the easy one. All you do is you take your r and your theta that's given to you in the problem, which is the numbers that represent the point in polar coordinates, plug them in here, you get an x, you get a y. It's very simple, bulletproof, and you have your Cartesian coordinates. Now the next one is a little bit more challenging, but it really isn't that much more challenging. Okay, so let me go ahead and write this down. To go from, okay, Cartesian, and just for a reminder, that's x comma y, to polar, and as a reminder, that's r comma theta. If you're given x and y and you'd like to go to r comma theta, let me go ahead and write it down in all its glory, and then we'll talk about it, okay? The way you would do that is, you just have to remember the following. R squared is equal to x squared plus y squared. We'll talk about this in a second. and the tangent of theta is equal to y over x. This is how you convert, okay? So I'm given x and y here, and I'm going to plug in x squared plus y squared. I'm going to get r squared, and I just take the square root of that, and I'll get r. So that's how I arrive at r if I'm converting to polar. And then I know what y and x are, so I divide them like this, and that's equal to the tangent of theta. So if I take the arctan, or the inverse tan, then I will get the theta here that I need in the polar coordinates, okay? Now, why does this work? Okay, I'm going to draw really basically the same picture right over here. Okay, here's your thing here, your x and y, and here's some point right here. So there's an angle theta involved, and there's r, okay? And what you're saying here is, let's talk about the first part here. This is the easier part to understand. R squared, which is this distance squared, is equal to x squared plus y squared. That is nothing more than the distance formula, okay? Remember what the distance formula is? You know, you might have learned that in algebra. The distance formula is equal to, the distance between any 2 points in the rectangular system is the square root of delta x squared plus delta y squared. The difference between the points in x and the difference between the points in y, square them, add them, take the square root. This is exactly the same thing. It's just I didn't write the square root here. I'm writing it as r squared is equal to x squared plus y squared. Because you're always measuring this from the origin, that's just the definition. The point you have here is always, the length r is always from the origin, so delta x and delta y are just going to be equal to the values of x and y of the point, okay? You square them, you add them up, you take the square root, and you'll get r, okay? You'll get r, okay? And another way to think about it, if you want to think about it, is also this is the equation of a circle. This is the equation of a circle, if you remember back to algebra, centered at the origin. X squared plus y squared is r squared. R is the radius, and that's exactly what's going on here. So I'm telling you 2 different ways to remember. This is pretty easy. You plug in your x and your y, and you get your r back. Okay, you take the square root and get your r back. This is also pretty easy because if you look here, okay, if this is a triangle, this is the side of a triangle, and this is the side of a triangle. Now, just the definition of the tangent with a right triangle here, because remember, this is a right triangle. Tangent of theta is equal to opposite over adjacent. Opposite is y, because this is y, and adjacent is x. So all I've written here is the exact definition of what the tangent is in terms of a triangle. Tangent of theta is opposite over adjacent. That's all it is. The only reason that this one's a little bit tricky is you really have to be careful about your quadrants, okay? And we'll see it when we get to the problems. But basically, when you're given an x and you're given a y, okay, remember back to the very first section on the inverse tangent function. So what you're going to end up doing is you're going to divide x by y, and you're going to take the arctangent to get the angle back. Well, arctangent, okay, arctangent only returns angles in the following range. Theta from negative pi over 2 to pi over 2. Okay, it only returns. So in other words, if you go to your calculator and you put any ratio of numbers here and you take the arctangent, it's only going to return values in this range, even if the angle actually lies in another quadrant. And that's just, you can go back to the inverse tangent and the inverse trigonometric function section and the DVD and read and kind of watch and see why that's the case. But the arctangent in a computer and a calculator or whatever is only going to return these values here. And these values, by the way, if this is x and y, negative pi over 2 is down here. Positive pi over 2 is up here. So it's really going to only return values in this half of the plane, okay? So when I divide y by x, okay, if I get a positive number, y divided by x is a positive number, the angle it's going to return back is always going to be in this quadrant because it's positive. And if whatever I divide by here ends up being negative, I'm always going to get an angle down here. Okay, but depending upon the actual values of x and y, the actual angle might be over here. And the only way to figure that out is going to be to actually look at the x and y values and figure out what quadrant you're in. So that may sound a little complicated, but we'll walk through it several examples and I'll show you. It's not that hard. It's just the main thing to remember here is when you divide y by x and you take the arctangent in your calculator, or if you do it, you know, in your head, just make sure the angle's right based on the values of x and y. That's all I'm trying to say here. You got to make sure, because your calculator is only going to return this. The actual angle may be over here, depending on the values of x and y. Okay, you can do this stuff all day, but it really is helpful just to work some problems. So let's do that now. Okay, what we're going to do is we're going to plot the point in these problems. We're going to plot the point, okay, which is going to be a polar point, okay? And we're also going to find another equivalent polar representation of the point. Okay, and all I'm trying to say here is we already talked about there's an infinite number of ways to write a polar point. You can keep adding 2 pi around and around and around, or you can subtract 2 pi, and you're going to get another representation equally valid. That's all I'm trying to say there. So let's go ahead and do it. Let's go ahead and say that we have a point. These are polar points, 1 comma pi over 2. And you were asked to plot that. Okay, so how would you do it? Well, here is xy. Okay, the first number is the radius, and the second number is the angle, pi over 2. Pi over 2 radians is right up here on the y-axis, and the radius was said to be 1, so this point is exactly right here. Okay, so the point is 1 comma pi over 2. And the reason it's up there is because the radius is 1, so I'm labeling this radius as 1, and it's up here at an angle of pi over 2. So I only took 2 numbers to plot that point. Now if I wanted to find another representation of that, all I got to do is add 2 pi to that, right? Or I can subtract 2 pi. I can do lots of things, but I'm just going to go ahead and add 2 pi. So if I wanted to do that, it would be 1 comma pi over 2 plus 2 pi. And I wanted to go ahead and add that up. It would be 1 comma, let's go ahead and add this up, pi over 2 plus, now I'm going to write this in terms of 4 pi over 2 because I want to be able to add these fractions. So 2 pi is 4 pi over 2. I just rewrote it so I could add them up. Okay, and this is going to be equal to 1 comma pi plus 4 pi is 5 pi over 2. So the question just said find another representation. It didn't say find them all because you can't find them all. You can, you'll be going on and on forever. Now look here, 5 pi over 2. How would you plot that if you were given this? Well, here's pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So you see it's the same point. It's the same place. That's why they're valid. So these two representations are exactly equal, or exactly equivalent, I should say. No, neither is better than the other. Okay. So what if I were given a point that's 4 comma negative 2 pi over 3, and I wanted to plot that point, and that's a polar, the polar representation of a point. Well, if I draw my coordinate axes here, x and y, then basically I need to start looking at negative 2 pi over 3. Now remember, any multiple of pi over 3 is going to be like 60 degrees, okay? So, and it's negative, so we're going to start going this way. So this is roughly 60 degrees, that's negative 1 pi over 3. And then this one over here will be negative 2 pi over 3. So it's going to be along, basically along this direction here. And the distance is 4, so you go 1, 2, 3, 4 units out along this vector here. So this is the point right there. So the angle is negative pi over 3, negative 2 pi over 3, and it's 4 units out. That's what you're doing right there. The point there is 4 comma negative 2 pi over 3. And if you wanted to find an equivalent version of that, of this point, the easiest way to do it is just to add 2 pi. 4 comma negative 2 pi over 3, and we can just add 2 pi to it. It's the easiest thing to do. Okay, so it's going to be 4 comma negative 2 pi over 3 plus, now I want to write this 2 pi over 3 in terms of something, now I want to write this 2 pi in terms of something right here that I can add together. So I write it with a 6 pi over 3, which if you do this division is equal to 2 pi. I just wrote it that way so I could have this common denominator. And so the final answer would be 4 comma negative 2 pi over 3 plus 6 pi there is going to give you 4 pi over 3. 4 pi over 3. And so the answer would be 4 comma 4 pi over 3, which is the equivalent form of this. So these are representing the same point. And looking back at my drawing here, I mean, it's a little bit misleading. I'm doing this all freehand. I mean, pi over 3 is roughly 60 degrees, which is here. So negative pi over 3 is here. Negative 2 pi over 3 is probably going to be something more along the lines of this instead of kind of flatter like that. So just in case you were wondering why I drew it that way, it's just because I'm looking at the board at an angle like that. Now, just a minute ago, we were looking at polar points and we were plotting them on the graph just so you can get a feel for that. And we were also finding equivalent representations by adding or subtracting 2 pi or 4 pi or whatever you want to do to get an equivalent representation. Now we're going to practice on converting from one coordinate system to another. And first we're going to start out with problems where I'm giving you the polar representation, r comma theta, and then we're converting to Cartesian. And you'll see that it really isn't all that hard, okay? So if I had given you a point square root of 2 comma pi over 4, This is the radius, it's just a number. This is the distance from the origin, and this is pi over 4, which is 45 degrees, okay? So if I wanted to draw that, just to give you kind of a flavor for what it looks like, okay? This is x, this is y, it's 45 degrees, which is pi over 4, and this point, I would just define it to be square root of 2 distance from the origin, okay, whatever that is in your calculator. I think it's about 1.4. So this would be square root of 2 comma pi over 4. So it's exactly a unique representation of this point right here, okay? All right. And this would be a distance of square root of 2 from the origin, okay? Now, if I want to do that, if I want to convert to find the x and y values here, remember back from the previous board that x is equal to r cosine of theta, and y is equal to r times sine of theta. You really should burn these in your head if you haven't already. You're going to use them so much. It's really useful just to go ahead and remember them. So the x-coordinate is going to equal r, which is square root of 2, times cosine of theta, which is pi over 4. So it's going to be square root of 2 times, what is cosine pi over 4? You should remember that that's equal to square root of 2 over 2. Okay? So x is going to equal, I should say over here, square root of 2 times square root of 2 is square root of 4 over 2. And because I multiply 2 times 2 under the radical, and square root of 4 is 2 over 2. So obviously x is going to be equal to 1. That's the x value. And y is going to equal to square root of 2 times the sine of the angle, which is pi over 4. And in this case, it's going to give you exactly the same thing. Square root of 2 times sine of pi over 4 is also square root of 2 over 2. So we've already done all this stuff, and we can say that y is also equal to 1. Okay, so this representation here, which is square root of 2 as a radius at pi over 4, is exactly equivalent to saying that x is equal to 1 and y is equal to 1. So if I were to go off on a sheet of graph paper and mark a point with 1, comma 1, okay, and then measure the distance to the origin, I would get square root of 2, which is a little bit greater than 1. If you take the square root of 2, it'll be greater than 1. That kind of makes sense from this picture. It should be greater than 1. Okay? So you see, converting from polar to Cartesian is easy. You just put it in there. As long as you know how to take the sine and the cosine, that's all you have to do, and it's pretty bulletproof. Okay? Let's do another one. Okay, let's say I was given a polar representation, which is 1.5, comma, 3 pi over 2. 3 pi over 2. Well, x is equal to r cosine of theta, which is equal to r, 1.5, times cosine of 3 pi over 2. Okay? What is the cosine of 3 pi over 2? Well, cosine 3 pi over 2, if this is your coordinate system, this is pi over 2, 2 pi over 2, 3 pi over 2. So the cosine of that is 0 because it lies along the x-axis, right? Okay, so obviously x is going to be equal to 0. X is equal to 0. Okay? Now what would y equal to? Y equals r times the sine of theta. So it's 1.5 times the sine of 3 pi over 2. And we just saw that if this is your axis, this is pi over 2, 2 pi over 2, 3 pi over 2. So it's down here. So this is going to be 1.5 times negative 1 because the sine of 3 pi over 2 is negative 1. Okay? And then that would simply mean that y is going to equal negative 1.5. Okay? Negative 1.5. So if I were going to write this down and just draw a picture of it, okay, x and y, okay, x and y, what I would find here, let's just plot these coordinates here. Now I know what x and y are. X equals 0. Okay, here's negative 1. Here's negative 2. What I'm saying here is that 0, comma, negative 1.5, x comma y, that's where that point is in the rectangular coordinates. Now also let's look at the polar representation. It's 1.5 is the distance from the origin. That's exactly matching up with this 1.5. And the angle is 3 pi over 2. Pi over 2, 2 pi over 2, 3 pi over 2. So you see they represent exactly the same point. Now given the final example problem of this type, if it were, and I'm doing a conversion from 4 comma negative 7 pi over 6, which is the polar representation, okay, then if I wanted to find the x-coordinate, it's going to be r times cosine of theta, which is r, which is 4, times cosine of negative 7 pi over 6. Now, you really have to know how to do your trig to find your sine and your cosine to be able to do that, because if you look here, where is negative 7 pi over 6? Okay, well, pi over 6 is kind of like 30 degrees. That's how I remember it. So here's roughly 30 degrees. So it's negative pi over 6, negative 2 pi over 6, negative 3 pi over 6, negative 4 pi over 6, negative 5 pi over 6, negative 6 pi over 6, which is negative pi, negative 7 pi over 6. So this is roughly over here. So it's about 30 degrees up from there. Negative 7 pi over 6 is up there in that quadrant. Why do you need to know that? Because when you take this cosine, you're going to have to know that. 4 times. What is the cosine of this? Negative 7 pi over 6. Well, cosine of regular old pi over 6 is square root of 3 over 2. But because we're in this quadrant, you're projecting on a negative cosine, it's going to be negative square root of 3 over 2. You have to know how to count in radians around the circle, and you have to know how to do your trig functions. And if you don't know, you should go pick up the trig and pre-calculus tutor to refresh on that. But you have to be able to do that kind of in your sleep in order to survive this. So x is going to be equal to negative 4 divided by 2 is 2 times the square root of 3. Okay, x is equal to negative 2 times the square root of 3. That's factor number 1. And then y is going to be equal to r times the sine of theta. And r is again equal to 4. And we have sine of negative 7 pi over 6. Now, again, the angle is in the same place. Sine of regular old pi over 6, if it were over here, is equal to, because it's sine of 30 degrees roughly, is 1/2. So sine of pi over 6 is 1/2. But you're in this quadrant over here, and so you're projecting against a positive y. So it's going to be the same thing, positive 1/2. So y is going to be equal to 4 times positive 1/2. You have to know where this thing lies in the xy plane to be able to figure out if your sine or your cosine is going to be negative or positive. So y is going to be equal to 2. Okay, so the angle, or I should say the Cartesian representation, is at negative 2 times the square root of 3, comma 2. If you were to plot that, then you would find exactly where that point lies. And this representation is exactly the same as this. It's just written a little bit differently. Okay, now just a few minutes ago we did several problems where we were given the polar representation. We put into our relations for x and y, and we were able to arrive at the x and y coordinates for the polar representation of that function. So we're going from polar to rectangular, polar to Cartesian here just a minute ago. Now we're going to do the opposite. I'm going to give you the rectangular version, the Cartesian version, and I'm going to ask you to give me the polar representation. So that's what we're going to do next. So if I had given you a rectangular point at 2 times the square root of 3, comma, negative 2. This is just an x value and a y value. That's all that is, okay? Now, the way you do that, remember, to find the r, which is the distance from the origin, it's r squared is equal to x squared plus y squared, okay? R squared is equal to x squared plus y squared, okay? So r squared is equal to, what do I have here? I have 2 times the square root of 3 squared plus negative 2 squared. Now what do I have in here? The 2 squared is going to give me 4, and the square root of 3 squared is just going to give me 3. Okay? And negative 2 squared is just going to give me positive 4. So r squared is equal to 12 plus 4, which is going to give me 16. Okay? And then to actually find what r is, which is what I'm going to need, I just take the square root of 16, which is 4. So r is equal to 4. So I'm halfway home, I'm done. Now, one thing I want to point out to you here is that anytime you take the square root of both sides of an equation, you really should have a plus or minus here. So this would be plus or minus 4. But, you know, since you're talking about a distance from the origin, you can't have a negative number there. So it's one of those solutions you throw out. So if you're one of these people that's used to putting plus or minus when you take a radical over something, that's right, but you just throw out the negative because you can never have a negative distance when you're talking about polar coordinates. It's always a positive number from the origin is the short answer, okay? So that is r, that's halfway home, literally halfway home. Now what we have to do is we have to find the angle. The way you do that is you remember that it's tangent of theta is equal to y over x, okay? So tangent of theta is equal to y was negative 2 and x was 2 times the square root of 3. Okay? So what you can say, tangent of theta is going to be equal to negative 1 over square root of 3. because you just canceled the 2's, okay? So all I have to do now is find out what this angle is, okay? Find out what that angle is, and the way you do that is you take the arc tangent. You could put it in your calculator, but really you need to become proficient at just doing this on your own. So 2 things you need to do here. You need to find out what the angle is that's going to give you this, and then you have to double check your answer against the quadrant that you know that this point is in. Now, just from, even without doing this, what quadrant is this guy in? I mean, you know, if this is xy, okay, I have a positive number for x, it's going to be somewhere over here, 2 times the square root of 3, and negative 2, that's somewhere over here. So this point is going to be somewhere over in this quadrant down here, okay? The point is going to be somewhere in that quadrant down over there. And you just want to make sure that whatever angle you get is going to give you that as the right answer. Okay, it's going to give you the right quadrant. And there are going to be some cases when your calculator will not give you the right quadrant. So that's why you have to be careful. So let's just say, basically the way you do these is you start marching around the unit circle and plugging in values until you find the right value. So let's just say if theta is equal to negative pi over 6, what will we have? Okay. If I did that, remember tangent is equal to sine over cosine, so it would be sine of negative pi over 6, if this were the angle, if this were the correct angle, over the cosine of negative pi over 6. Now let me evaluate that. What is sine of negative pi over 6? Negative pi over 6 is roughly right here, so it would be negative 1/2, because it's basically sine of 30 degrees. Down here below, projecting on the negative here, so it's negative 1/2, and then on the bottom, cosine of the very same angle, cosine of negative pi over 6, is projecting on the positive x-axis, so it's going to be positive, and you should remember from your trig, it's square root of 3 over 2. Okay, now the 2's cancel with the 2's, right? So what if this were the correct angle? What I would get here by taking the tangent, sine over cosine is a tangent, is negative 1 over square root of 3. So what I'm trying to say here is I shortcut a couple things, because if I'm doing this, you know, and I hadn't worked it before, and I know that tangent of a number is equal to negative 1 over square root of 3, I'm going to start picking values of theta, plugging them in to the tangent, and seeing when I get something that agrees. So if theta is negative pi over 6, we found that it does in fact give us what we said it should give us. Okay. Now this could be the right answer for theta, but the other thing we have to make sure is, does it agree? Okay. Does the quadrant agree? Okay. Look at this. Where would this angle be? Negative pi over 6. Well, positive angles are this way, negative angles are this way. Pi over 6 is roughly 30 degrees, so that does tell me that it's right there. So it's in the right quadrant. You see, this angle, negative pi over 6, lies down here. It exactly agrees with the quadrant that the point is actually in, x comma y. So, because they agree, this is your theta, and this is your r. Okay? So you would say 4 comma negative pi over 6 will be the answer to that question. And we're going to get some problems in a minute where maybe your first guess at the angle doesn't actually, isn't exactly right, even though it may look like it's right, and I'm going to show you how to identify that. So let's do that here. Let's say your point is negative 2 comma square root of 3 comma 2. That is your rectangular point. Now, I want to draw your attention to something. Let's go back and look at the previous problem. In this problem, x was 2 comma square root of 3, y was negative 2. In this problem, it's the same numbers, but now I've got negative for x and positive for y. I'm choosing this problem on purpose because I'm trying to illustrate something to you. You see, it's the same numbers, it's just that the negative is in a different place. Over here, y was negative, and over here, x is negative, but the numbers are the same. So we're going to go through the math in a minute, but because of the way we have defined r as x squared plus y squared, I think you can convince yourself, we'll do it in a second, I'm not shortcutting you here, you're going to get the same value of r, okay? So that part's okay. And then when you come down to this tangent, you're going to be dividing y by x, you're going to be dividing the same numbers, it's just that in this case, a different one is negative than in the previous problem, but because you're dividing them, you're still going to get negative 1 over square root of 3, okay? So you're going to get you're going to be tempted to calculate the same angles, all I'm trying to get at here. But you're going to see as we go through it that this angle is actually not correct for this problem. It's correct for this problem, but not for this problem, even though really the math is almost the same. So let's do that. That's sort of a prelude more than anything else. To find r, it's r squared is equal to x squared plus y squared. Okay? x squared is going to be this guy, which is negative 2 times the square root of 3 squared plus 2 squared. So r squared is equal to negative 2 squared is 4 times square root of 3 squared is just 3 because I dropped the radical, plus 2 times 2 is 4. So r squared is going to be 12 plus 4, which is 16, and so r is equal to 4 when I take the square root. So you see we did get the same radius. Okay, we did get the same radius, and that's because these problems are very similar. Now to find the angle, we just remember that the tangent of theta is equal to y over x. So the tangent of theta is going to be equal to y, which is 2, over x, which is negative 2 times the square root of 3. Okay, so it looks incredibly similar. It's just that in the last problem, the minus sign was up here instead of down here. But in both cases, I end up concluding that the tangent of this angle, whatever this angle is, has got to be equal to negative 1 over square root of 3. Okay, negative 1 over square root of 3. So the way you find these angles is you start marching around the unit circle calculating the tangents until you get the right value here. That's how you find the angle. But I'm cautioning you that when you do that, you just need to make sure that the angle you picked is in the right quadrant for the problem that you have. So we know from looking at our point that we know what quadrant is in. Negative x, somewhere over here, let's say, positive y, which is somewhere up here. So this point is actually up here. In the previous problem, the point was down here. You see why that was the case? The reason is because one of the points is one of the coordinates in x and y. One of the x's in the last problem, x was positive, y was negative. In this problem, x was negative, y was positive. So it kind of maps it to the other quadrant. But when you divide y by x, as long as one or the other is negative, you're still going to get the same value here. That the tangent of theta is equal to negative 1/3. So the way, if you didn't have the benefit of this lecture in front of you, you might just put this in your calculator and remember that the arc tangent in your calculator is only going to return values from negative pi over 2 to pi over 2. So that's negative pi over 2 to pi over 2. So it's only going to return angles over here, and it's going to give you an angle over here for this problem because here you have x is positive and y is negative. So the tangent of the theta is going to give you a negative right there, and it's going to give you an answer in this quadrant, which is what the other problem did, and that problem's not exactly right. So just going through the motion, because I want to make it complete, if you didn't have the benefit of this lecture, you might say, well, maybe theta is equal to negative pi over 6. Maybe that's the case, okay? Let's see if that's right. Then you would say, okay, well, tangent is sine over cosine, so sine of negative pi over 6 over cosine of negative pi over 6 is equal to what? Sine of negative pi over 6, we already did this stuff before. Sine of negative pi over 6 is negative 1/2, and we just did this before. Cosine of negative pi over 6 is like cosine of negative 30 degrees, is positive square root of 3 over 2. Okay, and we get excited here because we see the 2's cancel, and this is going to equal negative 1 over square root of 3. So you see, you might do this and you might say, oh, look, I found the answer because I found an angle so that if I take the tangent of this angle, I actually get back the negative 1 over square root of 3. So I'm done. I'm finished. I've completed the problem. The answer is 4, comma, and the angle would be negative pi over 6. But look at what you've done here. You found an angle here, negative pi over 6. But we know from the original coordinates that it doesn't lie over here. It lies way up here. So if you calculate an angle, or if you dump it in your calculator and you're going to get an angle in one of these quadrants here, and if you know by looking at the point, and you should always look at the point, that the actual point is in the opposite quadrant, all you have to do is take the angle you found, which does give you the right tangent, by the way, okay, and just add pi radians to it. You don't want to add 2 pi radians because that would just map it all the way back to where you started. You want to take it here and you want to add pi to it, which is going to map it in the quadrant you want. That is the short story there. So all you have to do is you'll say theta is going to equal negative pi over 6 plus pi. You're just going to add pi to it, and that's going to map it in the right quadrant. So it's going to be negative pi over 6 plus, and I got to write pi as 6 pi over 6 because I need a common denominator here. So then theta is going to equal negative pi plus 6 pi is going to be 5 pi over 6. So this is the angle, and this is the radius. Okay, so 5 pi over 6. Now, does that make sense to you here? 5 pi over 6. This is roughly 30 degrees. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. And my drawing's not exactly to scale, but it's roughly right, okay? So, short answer is, when you're doing this part where you're converting from rectangular to polar, getting the radius is easy. X squared plus y squared, get your value of r, but when you take the ratio of y to x and you calculate something and you're taking that arc tangent, go ahead and find an angle that works, but when you find that angle, always compare what you found, the quadrant that is in, to the actual quadrant of the point that you have, and if they're in the same quadrant, like in the previous problem, you got the right angle, but if the quadrant is mapped on the other side like this, then you're going to have to go back and add pi to it, or subtract pi from it, it's the same thing, to get the proper angle. If you put this angle on your test, it will be wrong, because this is totally wrong point. Okay, now the final problem is, what if I give you a rectangular point, and that's going to be negative square root of 2, comma, negative square root of 2. This is rectangular, x comma y, and I want to find the polar representation. Well, the first thing you do is you try to find r. So r squared is equal to x squared plus y squared. That's just the distance formula. So this is equal to negative square root of 2 squared plus negative square root of 2 squared, because here's y, okay? So r squared is equal to negative times negative gives me positive. Square root of 2 squared is just positive 2 plus, same thing here, positive 2. R squared is equal to 4, and then r is equal to 2, taking the square root of both sides. So I found my radius. Finding the radius is always really simple to do. You're always going to be able to find that really quickly. Now what we need to do is find the angle. So remember, the tangent of theta is equal to y over x, okay? So the tangent of theta is equal to y, which is negative square root of 2, over x, which is negative square root of 2. Okay? So the tangent of theta is equal to 1. Okay, the tangent of theta is equal to 1. So all I have to do now is go find an angle, okay? Go find an angle where the tangent of that angle gives me 1. And I think I have an angle in my head right now that I think may be the right angle. Let's find out. Let's say if let me change colors here, just to make it clear. Let me say, and this just popped in my head, let's just say theta is equal to pi over 4. Let's see if that's the right angle, okay? Tangent is equal to sine over cosine. So sine of pi over 4 over cosine of pi over 4, okay? Let's see what this is. Sine of pi over 4, you should remember, is the square root of 2 over 2. And the cosine of pi over 4, you should remember, is the square root of 2 over 2. So divide these out, you get 1. So I have found an angle, pi over 4, so that if I take the tangent of it, which is sine over cosine, what I get in the end is 1. So I really think I've got the answer, because tangent of this angle is 1. If I put this in my calculator, tangent of that angle, I will get 1 back. So I'm tempted to circle this. But the final step is always to go back and look at the quadrant. Okay, so here is your coordinate axis. Okay, now look at the point I have. It's negative square root of 2, which is somewhere over here negative, and comma negative square root of 2, which is somewhere over here negative. So I'm over in this quadrant here somewhere. Okay, now look at the angle I found. I found a positive pi over 4, which is squarely over here. Now if you put 1 in your calculator and took the arctangent or the inverse tangent, you're going to get pi over 4, because remember, calculators and computers are only going to return angles over on this side of the that side of the plane there. Okay, so I got pi over 4 because that was my first guess, but the actual point is nowhere close to that. It's actually pi radians away. So I need to add pi to map the angle I found all the way over here. Okay, so to find the answer, all I have to do is say theta is equal to pi over 4 plus pi. I'm just going to take it and I'm going to add pi to it. So that's pi over 4 plus, and I'm going to have to make this pi 4 pi over 4 in order to add them, because I want a common denominator. So the angle is going to be pi plus 4 pi is 5 pi over 4, and that is the angle. And to check yourself, let's look at it. 5 pi over 4. Let's start counting. Here's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, right here. That's the quadrant that you're in. So we do a quadrant check with the angle we found versus that. And if you just want to double check yourself, I mean, if you look at the sine and the cosine, if you were to plug it in here, okay, what is, if I want to take the tangent of it, what is the sine of 5 pi over 4 divided by the cosine of 5 pi over 4? What is that going to be equal to? Well, the sine of 5 pi over 4, which we know is down here, the sine is going to be negative. So it's going to be negative square root of 2 over 2. And the cosine, again, is going to be mapping it over here, so it's also going to be negative. Negative square root of 2 over 2. Negative divided by negative gives me a positive. So this is going to give me a positive 1. So what I've found here is the sine over cosine, which is the tangent of this angle that I have found, is equal to 1. Okay? I'm proving it to you. I'm showing you that this angle also has a tangent equal to 1, and it's in the proper quadrant. So you have to be on the lookout for that. So in this section, we have done a good introduction to polar coordinates and comparison to the rectangular coordinates that you've been using pretty much forever. There are certain applications, very common applications. You're going to have to get comfortable with polar coordinates. So don't just breeze through this and think, well, I probably won't use this. This polar stuff is actually very, very important, and you'll probably use it all throughout your school and definitely beyond school too. Okay, so basically it consists of two numbers, just like x and y, except it's r comma theta. A distance from the origin is r. Theta is just the angle from the axis. And you can have many different representations because you can continue adding 2 pi or subtracting 2 pi or 4 pi or 6 pi to get different angles. We also learn how to convert polar to rectangular and rectangular to polar back and forth, and we've shown several problems to do that here. So those are central skills that you're going to need to tackle the remaining sections in this class, and also in your furthering your education and also in your career.